Hello or welcome back. In the last video we have seen how to design the OLED controller, but as I discussed, your hardware implementation of the controller is not of much use. Each time you want to display something, you have to recompile your code and re-implement everything. So what we are trying to do is take a more hardware software co-design approach. We'll have the OLED controller which will be interfaced with the processor. In the processing part of the Zinc chip, and using software I will be able to control what should be displayed on the OLED display. Now to do that, we will retain the core part of the OLED controller. So I'm not going to change this part of the OLED controller. What we are going to change is this top module part. So what are this top module is doing? For example, providing the string and providing the valid signal, checking for the ready signal, basically the state machine. This part we will be modifying, and instead of using a state machine here, we'll be using some registers to do it. So so the initial step is exactly same as the steps that you use for developing the GPIO IP. So we will start with an IP generation wizard of Vivado. We will specify how many registers should be there, things like that. Then we will have to somehow interface those registers with my current logic. Now again, there is a standard way of doing it. For example, if I look at my OLED control, this is the data which has to be sent to the display, and as you have seen, we are basically sending the ASCII code for a particular character for doing this. So what I will do is, when I design an IP core, I will designate a particular register, and I will say I will store the ASCII code in that register, and that register value will be sent to the OLED display. Similarly, we have this valid signal. So I will basically say I have a register inside the IP. Usually we call it a control register, because that register is controlling how my IP is going to operate. And I will define like the 0th bit of the control register, I will make it 1 to indicate I have a valid data for displaying. And this signal, the done signal, what we'll do is we will connect this signal to another register. Let's call it the status register, because it's basically telling what is the status of the controller, whether he finished sending or not. And once the controller sends the data, he will make the status register 0th bit equal to 1. Now how the processor will manage it: if the processor wants to send some data, he will store that particular character in our so-called data register. Then he will make the control register value to 1. That means this signal will become 1. Then the OLED controller will send it, and once he sends it, he will make this signal high, which will make the status register bit 0 high, and the processor will be constantly monitoring this signal to check whether OLED has sent that data or not. Once he finds like OLED has sent that data, he will send the next data to the data register to send to the display. Okay, so this is the approach we are going to use, and most of the IPs, this is the approach. Like, you will have some control registers where the processor will set some control values. There will be status registers where the IP will show what is his current status, whether he is ready, not ready, sending data, things like that. And there will be some data registers where the processor comes and write the appropriate data. Okay, so that's the approach. So what I will do is I will go to tools here. So I'm in the same project where we stopped last time. This is the project from where you completed the OLED controller. So from that project itself, I am going to tool and create and package new IP. I'm choosing XE4 peripheral, and let's call my IP as OLED control. Okay, so let's say like IP for controlling OLED display. Number of registers, so basically we may need a control register, status register, and data register. 3 registers are enough, so we will keep it as 4 itself, which is the minimum number supported. In the interface here, we will still go with XI light interface because the performance requirement is not very high, so keep everything as such and click on edit IP. and finish. Now Vivado will be opening a new project. Okay, so one mistake I guess that I did was I didn't choose where that IP should be stored, and by default he used my previous selection, so he directly put it inside IP repo, but he didn't create a new folder here to store it. So maybe later we will move all these folders to a new folder and call it OLED Controller or something. Okay, but for you can, in the last window in that wizard, you can choose a new folder so that he keeps all of them there. Okay, fine. So this is the project automatically created for editing your IP. Okay, so let's keep all of them as such. So first thing I'm going to do is I want to bring all the source code, okay, all the core code for the OLED controller which we already developed to this project. So I will say add source, and I'll choose add sources, and I will browse and bring all those files here. So as I mentioned before, remember those files are inside the .sources folder in your previous project. So sources, okay, there are new. Okay, so these four are new files which we created from that project, and we imported the SPI controller for that project from another project. Okay, so that is sitting inside the import folder inside .sources folder. So I'm bringing that file also. Okay, so remember to check this copy sources so that he creates a new source, new copy of the source files for the new project, and say finish. So all those files are here. Okay, so first thing I'm going to do is making slight modifications here. For example, as I mentioned before, my plan is to bring this data to be sent from the register inside my IP core. So currently this data is coming from my state machine, so I want to move it from there and I want to connect it to the register. So I'm moving it to the input output port. So I'll declare input 7 down to 0, send data here. Similarly, input send data valid also. My plan is to bring it from the register, so I'll move it here, and output send done, that I am moving to the input output port, and I'm going to delete this entire stuff here and keep only the core OLED controller code. Okay, so basically the data to be sent should come from somewhere, the data valid should come from somewhere, and the send done will be sent back to from wherever the data is coming. Okay, so next what I'm going to do is I will take this top module and I will go into the IP source code. So this source code looks exactly same as the source code for GPIO controller. It's the exact same code, only the module name has changed because you gave a new name to your IP core. So go to that lower module which has the code for XC bus interfacing, and I am going to instantiate. You can actually instantiate wherever you want, but it's a good idea to instantiate it here towards the end, the top module here. Let me call it all at top or something. Now we are going to connect the signal. Now remember, previously the clock and reset, they were directly connected from the input output pins of the FPGA, but now that is not the case. This code is inside an IP, so this clock should be the XC clock coming to your IP. So I will take the XC clock, this one, and I am directly connecting it to the clock signal here. Similarly, reset. Now remember, axis uses active low reset. That's why it's written as axis reset n. So reset is low when it is active, but whenever we wrote our OLED controller logic, we are using active high reset. For example, here you can see if reset. So what I'll do is, when I connect the axis reset here, I will invert it and I will just connect here. Okay, so when this logic is in reset, I'm also in reset because I inverted it. Now SPI clock, SPI data, all these signals should be still going out of the FPGA, so you will have to wire them out till the top. So I'm just copy pasting them. I will copy paste them. All these signals should go out of the chip. So I will take their declaration from here and put them here. User port declarations, I'll put them here. Now I will copy it, and in the topmost module wherever this is instantiated, I will put it there also. And this declaration part, I will paste it in the top module also. Okay, so that they are connected to the top module. From the top module, they are connected here. Remove this comma. They are connected here. From there, they are connected here. From there, they are connected here. Now the only stuff which is remaining are these signals: the data, valid, and sender. Okay, so as I mentioned before, they should be connected to some of the registers. So this is what I am going to use. So I am saying, like, I'm going to use slave reg 0 as my control register, slave reg 1 as my status register, and slave reg 2 as my data register. So whenever processor wants to send some data, one character, the processor will be writing it to slave reg 2. Okay, so this is the logic where the processor is writing to the register. What I can do is I can just take it from there and just plug it here, send data. Okay, so makes sense. So when the processor writes to that register, that comes here. Now send data valid. As I mentioned, I'm going to use the 0th bit of control register to indicate I have a valid data. So I will go and take slave reg 0, its 0th bit. So when the 0th bit becomes high, this signal becomes. Okay, now remember, this data valid signal is used by the OLED controller to check whether there is a valid data or not. Now, the processor will make this bit 1 to indicate he has a valid data to send, and the OLED controller will send it. So we have the state machine for doing it. Remember, this is our state machine. And this one, this is where we are checking it. Now, the problem is, who is going to make this bit back to 0 once the OLED controller sends it? Okay, the processor can do it, but the problem is, again, the processor is software based, so he will make this bit 1. He will check whether the OLED controller actually sent that data by checking the status register. He may find like the data is already sent, then he will make it back to 0. But since it is software based, it takes several clock cycles to do it, actually maybe tens of clock cycles to do it. The problem is our state machine is running at very high clock frequency, so he will see this data valid high for many times for the same data. Okay, so that's the problem if we do clearing of this bit under software control. So we need to clear this bit under hardware control, so that as soon as the OLED controller sends the data, this bit becomes 0. Okay, so I need to move this logic from here. So I'm removing the slave reg 0 logic from here, and I'm writing it separately like our GPIO control. Again, always okay. Under reset we will make slave reg to 0 and else begin and end. So we have two cases. One is when the processor writes to this register. The second case is once the OLED controller finishes sending, he should make this register value to 0. So how do we know whether the OLED controller finished sending? That information is coming through this signal send done. So let me replicate it. So what I am saying is, if send done, when that signal becomes high, I will make it 0. Else if processor wants to write to this register, then whatever data processor is giving, that should go there. So I will say slave reg write enable is high and the address equal to 0, then this register will be whatever data is coming from the processor. You don't have to write that for loop and all. It's simply to complicate things. This is good enough. SXCW data, this is the data coming through AXI. I am storing it in the slave register when the processor wants to write, and the address to which he is writing is 0, which is my control register. Okay, so I can remove this one because you can have a register on the left hand side only inside one always block. I need to remove this one also. So basically slave reg 0, it is written by the processor and cleared by hardware. Again, this is a very common scenario you will encounter whenever you write hardware code. Now, the order in which you write here has some significance. For example, here send done signal has higher priority over the processor writing case, and it should be kept like this, because in case if the processor is writing to this register as well as send done is coming from the OLED controller, the register should be clear for the proper operation. You can think about it why it is so. So this order matters. Send done should be having higher precedence over writing from the processor. Now same way, slave reg 1. Slave reg 1 is basically telling the status of whether I finish sending or not. So that register will become 1 when send done is high, and the processor will be checking my register to check whether I finish sending or not. Once he finds the bit is high, he'll understand I have finished sending. Now the processor should clear that bit. Using software, you should make that bit to 0 before sending the next data. Otherwise, that bit will remain there forever, and when the processor tries to send data, immediately he will find like the data has been sent, but actually it is not. Okay, so the status will be set by hardware and cleared by software, just the opposite of control register. So I'm again taking the same code here, and I'm making slave reg 1 here. Under reset it is 0. If send done, this register will become 1. Otherwise, when the processor is writing to address 1, this register content will become whatever processor is writing. Processor will be basically writing 0. That we will control from software when we write the software. Okay, so here it is set by software, cleared by hardware. Here it is set by hardware, cleared by software. Okay, so again you have to move this from here, move this from here, move this from here. Otherwise, when you go for implementation, you will get multiple drive error. That's it. So we have completed the code. Now we can go to IPExact and we can merge all the changes. And we can repackage. Okay. Now there are some warnings here. So one warning is, if you go and check warnings here, OSPI clock associated bus interface bus parameter is missing. OLED SPI clock frequency hertz bus parameter is missing. So these two warnings are fine. You can ignore them. What Vivado basically says is you haven't specified at what clock frequency this OLED SPI clock will be running. You can provide this information so that when he goes for placement and routing, he knows what is the clock frequency so that he can place and route it appropriately. But even if you don't give this one, it is perfectly fine because he knows at what clock frequency the entire system will be running. Based on that, he might be able to derive and find out at what clock frequency this clock is running. And this warning is basically telling you haven't specified which interface is running at this clock frequency. Again, that is fine. This entire SPI interface is running on this clock. So if you prefer, we can group them together to a single interface and use it later. Maybe I will show it in another project how to do all these things when we use maybe Axie for full interface for high performance. So here you can ignore this warning package and we are done. Okay, so that project is closed. Now to test it and to develop the driver, I'm starting a new project. Let me call it OLED Controller Test. Yeah, I can close the previous project. Maybe one thing I will do is I will group all these folder into a single folder inside my IP repo. Let me call it OLED control, like our GPIO control. And let me move all of them inside this folder. Okay, this is our component.xml. Now, okay, we have it. Create a block design. Let's call it OLED system or something. Now the steps are exactly same as our GPIO. Okay, we have zinc processing system added. Automation. Okay. But if you try to add your OLED, it won't be displayed here by default. So we need to go to settings, IP repository, and browse and show that folder. So let me give this IP repo because both my IPs are sitting there. And he's showing like he detected two IPs, GPIO control from our previous project and OLED control, our new one. Okay. And now if I search for OLED, okay, that is here, connection automation. Fine, they are all connected. Only thing left is you have to make all of them external. Make external. Okay. Save it. Create HDL wrapper. Or you can test whether things are all correct. Validate design. Successful. Address editor. You can see address is already assigned. Okay, I can say HDL wrapper. Okay. It is generated. Now you can go ahead and generate with stream and export after that, or you can export now itself. I'm exporting now itself. Export hardware. Okay, so before that we need to generate so-called the output product. So click this and say generate output products. Last time you didn't have this case because you generated bitstream, then only you export it. So basically this generate output product, what it does is it fetches all the source code for all these IPs, either from installation directory, and if they are user defined IP, it fetches from the folder where you have kept these files, like in our IP wrapper folder, and he keeps all those files locally for this project. That is what is happening when you click generate output product. And you can export your hardware to SDK only after this step. Okay, so this is the minimum step required. When you click generate bitstream, this step automatically happens. So that's why previously you didn't see it. Okay, so now he's synthesizing, but parallelly we can export actually. So export hardware, but keep this option unchecked because my bitstream is not ready yet. And launch SDK. And okay, so as usual, we'll go to File, New Application Project. Let me call it OLED Test or something. And standalone, next, empty application, finish. So I'm going to write my software in a proper driver style, the same way we wrote it for the GPIO controller. I will have two files basically. I will have a header file where I will have the structure and all the functions declared. Then I will have another file, the source file, where I will define all these functions. Okay, so I'm choosing new header file. Let's call it oled.h. And here I will have my structure typed of struct OLED control. Let me call it OLED control. OLED control. So we have U32 base address here also. We'll include select types.h. So I'll have a int init. I have a function to initialize OLED, and it will take OLED control and the base address as the parameter. I'll have OLED say some function to write to the OLED, right? So we need to write some data to the OLED. We'll be sending one character at a time. So let me call it write character to OLED. Again, it will take two parameters, the pointer as well as a character. So let me call it char, my char or something. There is no separate function for reading from the OLED because you cannot read from the OLED display actually. Okay, so basically these are the two functions you need. But you may find you require additional functions. For example, you want to send one entire string to the OLED display. So this one is sending only one character at a time. But suppose you want to send an entire string, what you will do is you will take the string and you will send character by character from the string. So that function will be basically using this function internally. So let me call it print OLED or something. Again, it takes two parameters, pointer to the OLED and a character string. So it will be a char star type, pointer, character pointer type, and we'll be passing a string there. Okay, so basically we need only these three functions. If we need additional, we will add. So we'll have source file. Let's call it oled.c and we'll include oled.h here, and we'll define each function. So int OLED, init OLED. What this function does is my OLED base address, it will initialize, and let's return 0 to indicate finished initialization. Now write OLED. What we need to do. So remember, one character is coming, and as per our hardware design, this character has to be saved in our data register, which is the third register. So the address of that register will be base address plus 8. 0 is control, 4 is status, plus 8 is the data register. So first thing that you need to do is sil out 32 my OLED base address plus 8. To that you will write this character. After that you need to send the valid bit, which is the 0th bit of the control register. So for that, what you'll do, you will do sil out 32 base address, which is the control register. To that you will write 1. Okay, now valid is set. Now what the processor has to do is he should wait until this data is sent. So how does he know whether the data is sent? He has to read the status register, and he should keep on reading the status register until it becomes 1. That is how we designed our hardware. So let me declare another variable called maybe u32 status, and let me say, and initialize maybe to 0, while not status, as long as the status register is 0. What I will do is status equal to sil in 32, and we read from the status register, which is base address plus 4, the second register. Okay, so this is what we call as a polling mode. The processor keeps on reading from a register to check the status of a peripheral. Now this is a very inefficient way of checking for status. Now later we will see the idea of interrupts. So if we are using interrupt, the processor doesn't have to check for the status continuously. instead, once the peripherals, once the IP finishes whatever he's supposed to do, he will send a special signal to the processor saying like, I have done it. Then the processor can do whatever he wants to do. Okay, that is what we call as interrupt. We will discuss it more in lecture. Then we will modify our hardware and software accordingly. For the time being, let's use this polling mode. Okay, so once the status becomes 1, the processor will come out of the loop because now status is 1. So as I said before, the processor should make the status register back to 0. Otherwise, next time when you call this function, you will come here, you will immediately find the status is 1. But that status is not from the current transmission, that is from the previous transmission. So you need to do sil out 32 base address plus 4, and let's write 0 there. This completes the character writing. Okay, now our last function is print OLED. Okay, so this will be giving us one complete string, and we need to send that entire string. So my idea is I am going to take one character at a time from the string, and I will send it one by one. Now, if you look at the function, you are getting a pointer. So this pointer will point to the first element of the string. Okay, so it is enough to send this pointer. Then you can increment the pointer so that the pointer will point to the next element in the string, so on and so forth until you finish the entire string. Okay, so how does the code look like? I can say while this is not a null character, keep sending. Okay, again, you have to refer to some C textbook or resources to understand the idea, what it is basically doing. I can say while star my string, that means the pointer, the data pointed by my pointer is not equal to 0. I'm going to call this function, and I will pass star my string here. So star my string stands for the data pointed by the pointer. If you just write my string, this is the pointer, that means it represents the address. Okay, star OLED. Okay, so write OLED. Okay, so this should be the pointer to OLED. Okay, OLED. Don't put star OLED here because this itself is a pointer. So if you put one more star here, the whole idea changes. It represents a pointer to a pointer. Okay, but you have to put a star here because this is a function parameter declaration. So you need to say like this variable represents a pointer. That's why you put pointer here, star here. So this itself is a pointer. So just pass it here, and this one is star my string. And once it is done, so he will go to this function, he will send the character, you will come back here, the pointer should be pointing to the next data. So you need to say my string plus plus. Here don't put star because you want to increment the pointer, you want to increment the address. If you put star here, that basically means increment the data pointed by the point. That is not what you want. You want to increment the pointer itself, so it should be like this. Okay, so that's it. So these functions are sitting inside io.h. So we need to modify it like that. Okay, so now let's write our main function, which will be used for testing everything. Let me call it main.c. So here we of course need OLED.h. We also need xParameters.h. We have int main, and first thing we create an OLED controller, my OLED. Next we call the init function. So you need to pass the address of the structure, and base address we need to take from x parameter. So this is the base address. Now we need to send it. So I'm planning to print again hello world, so I'm calling this function print OLED, and first one is the pointer and second one is the string you want to. So maybe I will declare the string at the top. So let me change casta. My string is hello world. Okay, so this is one way of declaring string in C. There are other ways also, but this is good enough. So my string and returns. So that completes our software. So for hardware design, now you will run synthesis. Once synthesis is done, you will open it. You will assign the pin constraints for the OLED display. So you don't have to constrain clock and reset this time because they are coming internally. Then you will go ahead and run implementation and generate bitstream. So I have already completed them. Now let's test it. So you can either re-export your hardware from here, export hardware and include bitstream. This time you check this option, so the bitstream is also copied to the SDK and you can run everything from SDK. Or it's also possible to program your hardware from Vivado and just run the software from SDK. So this time let me show how we do it. So I'm not exporting bitstream this time. So when I click this program FPGA here, there is no bitstream listed because we haven't exported. So when I go to run configuration this time, again I will choose this option. I will choose standalone and just keep these two options clicked. Run PS7 init and post config, and under application choose the application. Okay, apply close. And first thing is you need to program. So I'm going to program from Vivado. So I will just program it from here using the bitstream and make sure the blue LED is on. Then I will come back here and I will just run the software from here. So run configuration. First time we need to click from here, run, and the software runs. And I can show you the output. Okay, you can see it is showing hello world, but like our previous one, lot of other pixels are also on because it's storing data in some GDRAM. So we don't know like what is the default value in those GDRAM. So maybe that's why other pixels are on. So one thing now you can do is, since you have a software here, I can write a function void maybe clear OLED, which will basically clear the entire OLED. Okay, so let's write this function also. So what I have to do is I will go here and write the body. Okay, so basically I need to clear the entire display. That means I will send how many bytes? I have 4 pages and each one 128. So 128 times 4 character I will send, and all of them I will make 0. Okay, so U32, let's call I for, let's say I equal to 0, I less than 4 times each one 128. So that is the total capacity of OLED. 120 8 column. Oh, my mistake here. We are dividing it into 8 by 8 pixels. So how many characters are there in one row? We have 128 by 8. We have actually 16 character in one page. Like that, 4 pages. Okay, 128 is the total number of column, but our display is 8 by 8. So it takes 8 column for one character. So I need to count number of characters. 16 characters and 4 pages in total. So 64 characters in total. So less than 64. I will do right OLED and my OLED here, and as the character I will send this empty blank. Okay, so that gets written to the OLED. Now what I will do is I will take this one, and before printing, after initialization, before printing, I will just call this function so that it clears the entire display. Okay, now let me run it once more. Okay, let's see camera, and now you can see hello world, but it's coming in 2 lines. You need to go and think why it is happening. Let me give a clue. Each time when you run your software, your IP core is not getting reset. Okay, so you remember the state machine inside the OLED, which has a column address counter. So each time you send a string, the string will be displayed at the next column from where it was displayed last time. Okay, so that's why we already had hello world when I ran the software previously. So next time when I run hello world, it will come after the previous hello world, after the position of the previous hello world. That's why it is coming like that. But our clear OLED function is working. That's why you will see like random pixels are not on. Now you can add more features to the software. You can add more functions where you can exactly specify on which page it should be displayed, which column should be displayed. Based on that, you will have to send dummy empty characters before printing your actual string. Or you may modify your hardware. Again, you can have additional registers where you can specify the page number and the column position, and your state machine takes the page address and the column position from those registers. Instead of, currently we don't have such control. It simply increments each time we send some data. So instead of that, he takes data from these registers and use those registers to decide from which position he wants to display, so that you have better control. That you can do. Another thing that you can do is like our GPIO previously, you can take your software from here and store it here, OLED control, in the driver folder here. So instead of these two, you delete these 3 files and replace them with these 2 files, actual driver, like this, and you can delete them, and you have to go and repackage your IP this time, so that next time when you export software, these drivers are automatically included in your SDK. Okay, that is another thing that you can do. And maybe another thing that you can do is in your hardware, you can remove the entire OLED controller and keep only the SPI controller there, and connect registers directly to the SPI controller. In that case, all the initialization command, everything has to be sent from the software. So your init function will basically send all those initialization sequence to the SPI controller. Then it gets initialized. Then you will again send the command for setting the page address, column address, etc. Then you send the actual data. That's also possible. So in that case, you won't have the the OLED controller in hardware, that is more or less completely in software, but you will have only the SPI controller in hardware. So that's also possible. So I guess after this tutorial you have a better idea about developing IP core. So you will always develop your core logic first. You will test it, simulate it, and even test on hardware sometimes to make sure it is working fine. Then you create your IP template, then integrate this core logic with the IP template with the help of the internal registers, and you connect them accordingly, and then you write your driver. Okay, so that's it. Thank you.